the subject here is generative models and probabilistic graphical models. Both of those are phrases that you heard today and yesterday. And so we're just going to come back now and say actually what they are a little bit more definitively. And then, as I said, we will scribble and talk about it together. Okay, so you have seen Bayes' theorem, and you have seen the prior and the posterior, and I'm not sure that you have seen the word sampling distribution before, but that's just another way of saying the likelihood function, which reminds us that it is a probability distribution. So I'm going to try and say likelihood just to not be confusing, but you might also see sampling distribution in the slides, and it just means exactly the same thing. Okay, so I think the key message is that, and this has been maybe danced around a little bit in the last 2 days, if we're actually going to write down expressions for what these things are, then at least in our brains, we need some kind of approximate vision of how the data that we have on our computers came to be, all the way from out there in the universe, something happened, and photons were emitted, and they propagated through space, and through the galaxy, and through the atmosphere, and through the telescope optics, eventually becoming numbers that were recorded on my hard drive. So hearkening back to Tall Adam's introduction yesterday, data are constants, right? I'm going to be a little bit faster and looser about it and say that if we take the constants that came from the telescope directly and we do something fully deterministic to them that has no uncertainty associated with it, or at least that we claim has no uncertainty associated with it, I'm still okay calling that data. So I'm just going to be a little bit bad in that way. But nevertheless, at some level they are models. And so our capital M model has to account for the physical processes that are happening out there, the instrumental effects, whatever they are, the measurement process itself, and any calculations that we did to the raw numbers before calling them a data set that we're not going to fit a model to. This is the ideal case, and of course in practice, most of what we do is taking shortcuts to this, but this is where we start. Okay, so the generative model, again, phrase that you've heard before, is the joint probability distribution associated with all data and all model parameters. So P of data, comma params, remember the comma means and together. And you have seen that that can be factorized into conditionally independent pieces in 2 ways. One of them is the way which is written there, P of params times data given params. It could also be equal to P of data times P of params given data. But this is the way which is familiar by now because this is the prior times the likelihood, right? And not too surprising because it's the probability of everything. It includes all of the modeling information that we need to do inference. Of course, that's the posterior right there. It also contains all the information that we would need if we wanted to create mock data according to whatever experiment we're doing. So what are they useful for? Coming on the end of the second day, this is possibly a silly question, but of course it is useful for doing inference, because we need to know what the prior is, and we need to know what the likelihood is to do inference. But there's also some utility to being able to generate fake data according to our model. You might want to use that to test your inference, so create a data set that you think looks like the one that you have, or in the case of something like LSST, like it looks like the one that we think we're going to have. So that we can develop our analysis codes, run on some pretend data set where we know what the right answer is, and just make sure there isn't a bug somewhere that we can get the right answer. It's also useful for checking our inferences, and this we'll come back to on Friday morning. So what you can do after fitting a model is generate a data set according to that model that you fitted, and you can ask whether it actually resembles the real data. And if it does, you can say that the model is an acceptable description of where the data come from, and if it looks radically different, then it probably isn't. But we'll come back to that. So in full generality, all I can talk about is P of data and params, right? But that's not super useful. But usually, and this of course always depends on the specific problem that you're dealing with, but usually it can be factored in very useful ways. And this is where the connection to PGMs, probabilistic graphical models, comes in. So a PGM is really just a sketch that tells us about the structure of this abstract thing that's up there on the board. So the way that I like to think about it, and this is not a perfect analogy by any means, but I think about PGMs as the statistics version of the free body diagram that hopefully everybody remembers from freshman mechanics, and you might remember also TAing freshman mechanics or something like that, and trying to convince students that they should draw free body diagrams, even though they insist that they don't need to. So here's me. I'm going to tell you, you should always draw a PGM, and you're probably sitting there thinking, no, I don't need to. But you should, because just like the free body diagram, so many mistakes will be caught at an early stage if the very first thing that you do when you have a new inference problem is draw a little picture and make sure that you understand the structure of the model that you're trying to fit. Those words will probably make more sense once we've seen an example. So let's do an example, and I'm first going to say a bunch of words out loud describing sort of the scenario for this problem, and then write down not equations, but relationships with Greek letters in them, and then we'll look at the PGM and we'll see how all those things connect. So, we haven't seen a lot of data, like actual data, from the sky, which is weird. But here's an image on the left. This came from a telescope. It's like, wow. Not directly, it's processed, but anyway. So there's an image. It so happens that it's an X-ray image of a galaxy cluster, but that's not really terribly important. And this is just a zoom in of something sort of right up there to show you that there are pixels in it. And they have different values. It's not a nice, smooth thing. There's some kind of noise. Okay, so here's actually what I would say is the very first thing that you should do when you sit down and you say, I have data and a model and I want to fit them. Ask yourself, what exactly is the nature of the data? In this case, the data is a number of counts associated with each pixel. So how many times was that pixel activated in an integration of some length? So here's me telling you in words how this data set came to be. Not in full detail, but in enough detail. So there's an object out there. We can agree on that, I hope. I'm not going to give you a course on galaxy cluster astrophysics right now, so we'll just say, pretend that I have a model for physically what it is and how it generates light, and there's some parameters theta associated with that, and we'll leave it there. From theta, whatever that is, we can invoke physics and make a prediction for the average flux that we receive here on Earth as a function of position on the sky. So there will be many pixels k, and if we know theta, then we can predict what the average flux at each of those pixels is. Let's say coming into the telescope. Given a little bit more information like the exposure time and stuff that I won't bother writing down, but the collecting area of the telescope and the efficiency and that kind of thing, things that are just multiplying and dividing by constants, hopefully, we could turn that average flux into an average number of counts that we expect as a function of pixel position. Yes? So by the way, every time I say determined here and here, I have in my brain there's an equal sign. So there's no additional random variance associated with going, say, from the model given by theta to flux and from flux to an average number. In a real problem, there might be, but in this simple example, we're just going to say one determines the other determines the other. But in the last step, there definitely is some random element to it, right? So we have an average number of expected counts from this model, but we know that when we actually do a measurement, what we get is a Poisson random number. So we'll have that average, and then the data that we get, we'll just call them capital N. With me so far? Okay, cool. So even just trying to describe it in words, you might have noticed I basically made a bulleted list. Well, I literally made a bulleted list. And what it was describing was conditional relationships. So this is going to say more or less exactly the same thing, minus the astrophysics parts. It's just telling us what is in this model and how do those things relate to each other. So I said there was an object parameterized by theta, and so there are parameters theta And in general, of course, they're going to have some prior, so we'll just say that. Notation. In physics, the squiggle sign, I don't know if we've seen this before in the last couple of days. So let's just say in physics, there's this squiggle sign, or the tilde, and that usually means to other physicists, left-hand side is kind of sort of like right-hand side, or is right-hand side to this power, give or take. In statistics literature, that is not what it means. It has a very precise definition, which is left-hand side is a random variable that is distributed as the PDF on the right-hand side. So we have to physics part of our brain, a statistics part of our brain, and we have to keep this straight when we talk to the right people. I'm going to use this left-hand arrow to denote, and I don't think that's a standard notation, but that will denote things that are not random. So, well, we'll get there in a second. So there's some theta, has some prior, and then for every pixel in our detector, here's what we've got. We have, based on which pixel it is, and that model for the object in the universe, a deterministic relationship, so these things determine exactly prediction for the flux of that pixel. And similarly, that flux and some constants like the exposure time determine exactly the average number of counts predicted for that pixel. And then finally, the number that we measure is a Poisson random variable based on that average. So exactly what I said in words, now in slightly more compact notation. So here's a picture that says most of that. It doesn't have all of the details, like the word Poisson does not appear anywhere, even in code in this, but it tells you about the same structure which is in that bulleted list. Namely, what is connected to what. But let's just take a step back and go through the convention of how these things look. And there are, unfortunately, in some of the details, there are multiple conventions. The basic ones on this slide are pretty solid, but you may see slightly different conventions as far as when are things shaded or colored or not colored or that sort of thing. I like to stick to a convention that you can actually draw with a pencil on paper, so there's no fancy coloring or shading or anything. Anyway, so ingredients of a PGM, which you might occasionally see referred to as a directed acyclic graph. If you talk to a mathematician, they'll say that. So 3 main ingredients. There are nodes. Those are the dots and the circles in this diagram. And those represent parameters and probability distributions associated with those parameters. There are edges in math speak, which are the arrows, and those will basically represent links between parameters, conditional relationships. And that rectangular thing that was subsuming some of these is called a plate. And that's telling us that there are model components that are repeated in a conditionally independent way. Those words, again, just give us a second and maybe they will make more sense. But first, I should point out, there was more than one type of node in that thing. They're all related to each other. So if you see theta in a circle, for example, that's sort of the standard thing. It says, here's a parameter, it has a name, and there's some PDF associated with it. So it's something in our little bulleted list, it would be on the left-hand side of a twiddle sign, somewhere in that. There are points or filled circles, which mean exactly the same thing, except that specifically the PDF in that case is a delta function. So that's just a really fancy way of saying those are parameters that are fully determined by other parameters, by some equation with an equal sign in it, and no additional randomness. It's just convenient to be able to directly see that. And then there was one of them, which you'll see again in a second, which was in a double circle. And those are also random, but that's a special symbol saying this is the data. So if we're doing inference, then those quantities are atom, constant. Thank you for using the microphone. But if we're generating data, then of course we're going to have to generate those values randomly. Hence the circle, but a slightly different kind of circle, basically. So here's the whole thing again, and you can see it has all of those pieces that I just mentioned. Now, The generative model for this particular problem is this horrible joint distribution here, so theta t, and for every pixel there's an f, a mu, and an n. And the claim that I'm going to make is that this diagram, or the bullet lists from earlier, are telling us that there's a sort of uniquely convenient way to factorize this into conditionally independent pieces. So you will remember, of course, because we've seen it only about 1,000 times in the last 2 days, that this thing, in general, we can decompose as p of a, p of b given a, or totally acceptable p of a given b, p of b, right? So there's many different ways that I could factorize that generative model into different pieces. But this is telling me a particularly intelligent way of doing it, I hope. That's what I'm going to claim. And I'm going to ask you to think on your own for 30 seconds or so. And after 30 seconds, put your head together with the person next to you and see if you can figure out what on earth I meant by that statement. And then we'll come together and sort of pool our ignorance. And you can hopefully collectively tell me what I meant, because I'm not entirely sure. And if that's not enough, the next question will be, what does all this imply in terms of how we would go about doing parameter inference, how we go about doing the generation of mock data? So 30 seconds, go, and then we'll come together. Okay, it seems like many conversations have petered to a halt, which is fine. Anybody want to hazard some sort of guess as to what on earth I meant by that? I realize it might have been a little bit of a jump forwards here. Would you like to sit silently for the next 68.5 minutes? Seriously, there's no stupid answer to this. Go ahead.
Well, we don't have the whole thing, but I think a piece of it is something along the lines of, if you're trying to figure out something about, say, mu, and you're saying, what is p of mu given f and t, you also know something where you can say you have some p of f given theta, because f only depends on theta in the way that this diagram is going. So I think one of the factors will be p of f given theta, and you'll have to multiply that by something else.
That's exactly the idea. I mean, you basically started breaking it down into the logical pieces, essentially. And I mean, this is not, it's not such a complicated concept. It's just, this sort of structure is telling you fairly literally, as I break this down, there's going to be something that has p of, say, mu k, given other things, and I can write that on the right-hand side of the vertical bar. There's just going to be f and t. I could write other things there, but they would not actually appear in the expression that I substitute in, so it would be kind of silly. That's essentially it. Let's see what I wrote down so that I make sure that I don't miss anything. Yeah, so the key here is that it is showing us the conditional dependencies. And so anything that it isn't showing us, any link that isn't there, is basically telling you you have conditional independence. What this means in the case of let's do generating mock data first. Basically what it's telling you is a flow diagram for, what are the lines of code that I would write if I wanted to come up with a fake data set nk. I would first magically, from my prior, pick a value of theta. Then for all of the pixels, I would calculate the fk and the mu k, and then for all of the pixels, I would generate an n from a Poisson distribution, right? Of course, that same flow diagram doesn't apply to parameter inference, but it's still telling you the pieces that you can sort of chunk together as individual calculations when you put together your posterior distribution in code. Does that make sense? So here, we can Now fill in, if there's enough space, the rest of this line. I'm going to do a very annoying thing, and I'm going to stand here with a piece of chalk and just write what people tell me to write. So you don't have to worry about the microphone because I'm just going to write it down. But let's do this factorization for this problem together. Yell something out.
Probability of f sub k given theta.
Okay. I agree, that will definitely be a term here. Just yell. Yeah. Ah, good, okay. Starting from the beginning, I like it. What else? Yeah. Very good. I think there's a couple more things. Oh yeah, probability of t. Good call. I always forget the t. All right, let me finish us off here. Let's not forget n. K given mu k. And I attempted to leave a little bit of space here. Can anyone guess why I did that? This would be the Poisson distribution P of n k given mu k. Now the space was, sorry? Yes, a big product, thank you. Or a sum in log space, whoever said sum. So, all right. And this is why you should take your own notes and not try and take a picture of the board, yeah?
Could you split apart probability of mu sub k p of f sub k into like f of like the probability of f of k is equal to that one, so f of k given theta. So could you break that apart to make it a square term? So you're just calculating the one piece.
So the question was, actually I'm not sure I understood, but can I combine these two things in some way?
I guess split apart the second term so that you can then just have a squared term. I don't know if that would simplify the calculation of the mu sub k probability.
I don't understand what you mean by a square term there. But we will talk about simplifying this in a couple of minutes, so maybe we can come back to it. Yeah. Can you use the microphone? Sorry.
Why is P of t in the sum?
Oh, because, well, it's a product, so it doesn't actually matter where it is. And it's there because that's the order that people suggested them. But because it's a product, I mean, it's not like it's being repeated that many times. It can go anywhere. Yes. I would put it out here myself just because it's outside of the plate in the diagram, right? Okay. Are we all reasonably happy with where this came from? Okay. And if you, yeah.
So I'm just curious, why is, let me ask the right question here. Why is P of mu, is there not explicitly theta in the given portion of that statement?
Because there's no direct conditional dependence of theta in mu. In other words, what this is saying is if I know t and f, that's enough for me to fully describe the distribution of mu. There's an indirect dependence for sure because f is connected to theta.
So you can say
Microphone? Microphone, please.
K given t and fk and theta.
I missed whether you said can or can't.
You can't say you can't say that. Like for me, I would say probability of mu k given t fk and theta.
You are perfectly welcome to write a theta here if you want to.
Okay.
But when it comes time to substitute a real expression for this, it won't have a theta in it. That's what this is saying. So you're also perfectly welcome to not have a theta in it. Okay, let us carry on, and if there are remaining, okay, last question.
Maybe we'll cover this later, but are there things that you can't represent with PGM? Say if you have seeing, and then what you get in each pixel sort of depends on all the pixels around it.
Yeah, there are certainly things that are inconvenient to represent with this sort of thing. So this is explicitly saying that there's a lot of stuff in each pixel which is independent of other pixels. Something like seeing varies across the field, but not in a fully independent way in each pixel. I think that's what you were getting at. So one would probably, some kind of model for seeing could be placed outside of here. Everything which is still inside is fine as far as being independent. But yes, more generally, it's true that you sometimes run into situations where you'd really like to be able to break things down like that, and you just can't. And you wind up doing something stupid like having no plate, and there's just an FK vector in a circle or something. So this is not, this is not some perfect thing. It's just a useful tool that helps a lot of the time. Okay, so we said all of that. Stupid question number 2, which again, talk to your neighbor for a minute or so. How are these two PGMs different? And what does the difference mean? And again, there are 2 contexts to have in mind here. One is inference, and the other is coming up with fake data sets. I feel like there might have been a conductor up here going like this. So it sounds like we're done. 1 minute and 30 seconds. Okay, so anybody, in the context of doing inference, what is the difference between these 2 things? Okay, well, first of all, visually, what is the difference between the 2 things? I think we probably agree that there's a circle around that theta and a dot in front of that theta, right? Okay, so if we're doing inference, what does that distinction tell us? Oh, sorry, yeah, go ahead.
All right, so I might have the wrong idea about this, but I would say the right is more of a frequentist view where theta is a constant, and the left is a Bayesian view where theta has a prior, it's a random variable itself. But I'm not sure if that's like the right.
That was far more sophisticated than what I had in mind as an answer. But a fair comment, in fact. So yeah, the difference here is just on the right, I'm claiming that I have perfect prior knowledge of theta. And that's it. And if you were a frequentist, that's effectively kind of sort of what you would be doing. In a weird, I don't understand frequentism myself. It just doesn't make sense. But yeah, I don't know of them using these diagrams either, so it'd be good to ask somebody if they know how they would represent that. And on the left, I'm saying that I do have some prior uncertainty on theta. I'm not saying what it is, but it's there. As far as just the procedure of generating fake data sets, if that's what I was interested in doing, what's the difference? It's not a trick question, yeah.
I assume that if you're generating data, the difference is that in one case you're just generating with a certain set of parameters, whereas in the other you're probably generating a range of data with a range of parameters.
Yes, exactly. Yeah, this as I was trying to convey, this really does translate more or less into lines of code or functions that you would write. So on the left-hand side, we're saying the very first thing I'm going to do is come up with a value of theta, and it's not going to be the same for every data set that I generate, presumably that being something that I want. And on the right, we're saying, no, it's going to have this single model. Everything now is fixed other than the data, and we're just going to generate lots of different Poisson realizations of the image of this fixed thing. Nothing more than that. And of course, if I'd given you instructions instead of pictures, then that would have been more clear. Okay, so on to simplification, which was mentioned. There are some ways in which this example is possibly too silly. because I went ahead and, we wrote out, oh, it's already there. Well, we wrote out this whole thing, and several of the terms in it are delta functions, we know, because we understand that the dot means a delta function. So this is a delta function, and this is a delta function, and this is a delta function. And of course, by now, we all understand that everything that we do as data analysts is an integral. And as physicists, we know what happens when you integrate a delta function very well, right? It just magically goes away and fixes the value of something else. So of course, we can do that. And what this very long line is showing you is basically, we could equivalently, we have this generative model here. We could equivalently scratch out the t and the f and the mu, just do those marginalizations, those integrations analytically in our heads. And what we would have at the end is possibly on the next slide, is that, right? So lots of things go away, or to put it differently, lots of things are hidden. So this is a simplification. I'm not going to say it's a good thing or a bad thing to do this. If this is embedded in some kind of much larger and more complex model, you probably don't want to be carrying around all of these mu's and f's and t's and just making your life complicated. On the other hand, every time you simplify in a way like this, as we know, it's an opportunity to forget to do something later on. So it's just, it's the usual trade-off. However, this does have the advantage that it makes it more explicit that what we have here is the prior times the sampling distribution for the data. Sorry, times the likelihood function for the data. Yes? Okay, and I have already said that. All right, this is the last silly exercise, and then we have real exercises, and maybe we'll take a break in between because it's been 40 minutes. So, again, working with your partner, we have two models here, and let's try and this is where having just one or two sheets of paper is helpful. Scratch out sort of the bulleted list of this has a left arrow to that, this has a twiddle sign to that, that's represented here. And the factorization in this sort of a form that go with both of them. And in a couple of minutes, we will reconnoiter and figure out what we have figured out. Okay, everybody, are we ready to pool our ignorance and try and figure this out together? I'll take that as a yes, since some of the room quieted down. Okay, let's deal with this thing on the left-hand side. And it's up to you. So I'm, again, just going to stand here dumbly and be a robot with a piece of chalk. And people can either suggest a way of factorizing the generative model or suggest something in terms of sort of the bulleted left-hand side, twiddles right-hand side list for this left-hand PGM. Anybody can get us started. Don't worry about the microphone because I'm going to either repeat or write down whatever you say. P theta. Okay, so we're going with the factorization business. Okay? P of C given theta. Okay. Good. All right. We're becoming more confident as we go along. Okay. And is there an incredibly simple way that I can simplify this? That's a silly way of putting it. Is there an instant simplification that I can do here? Yes, this one is a delta function, and if I want to, I can just go like that. Okay, let's go through the exercise of also writing down the bulleted list, just because that's sometimes a useful way of organizing our thoughts, at least I find it. So I'll get us started. This is going to be a little bit silly, possibly. Well, I'll start anyway. First one would be theta goes as something prior, right? This thing here, this is just P of theta. There's nothing it's conditional on, so Based on the diagram, we don't know what that PDF is, but it's something. So there should be 2 more lines here because I have 2 more parameters. I heard the beginnings of something. Yeah.
C is a data function.
Mm-hmm.
You will only get non-zero value for specific value of t, right? Because if it is a data function, then
Mhm.
and we have considered that probability, so wouldn't that be like p of d of c, right?
Oh, I see. Okay. So when we say this is a delta function, what that actually is meant to imply is this would be, in fact, the board's going to be confusing. Okay. So P of C given theta would be some delta of C, nope, that's not a C, C minus, I don't know, some function of theta. Does that make sense? I mean, so again, based on this, I don't know what that is. It doesn't mean that there's only one value of C which is acceptable. In general, it means that for a given theta, there's only one value of C which can exist. Yeah.
C backwards arrow theta.
Yes, exactly. So C is something depending deterministically on theta. So if I'm actually writing code, this is going to be C equals something, where this is not a random draw of anything. Okay, last piece. Only one piece left.
Yes, wouldn't it be D left arrow C theta?
D left arrow C theta. What do we think? Yes, thank you. I'll repeat it because I could barely hear you up here. So this is not, according to the PGM, a deterministic relationship. So what should I have instead of the arrow? The wavy thing. Good, wavy thing. Okay. Yeah, so all right, let's group all these things together. Personally, I find this to be sort of a easier way of writing it down, easier to grasp than trying to do this. But it's a matter of taste, right? Okay. Now, the right-hand diagram. How shall we start? I'm going to stand over here on the right, actually. Volunteers. Who started talking? Continue. P of theta given D. Good. P of C given theta. Okay. Huh. Okay. So I might not be a mathematician, but I'm pretty sure this is not a product of probabilities that I'm allowed to write down. Does anybody have an objection to what we've done? Yes, okay. What is your objection? You nodded.
Well, I have an objection. I don't know, but there's not. It doesn't start.
It doesn't start anywhere. Right. Remember I said this was, PGM is an example of a directed acyclic graph. Acyclic, of course, means no cycles. This is a completely nonsense diagram. You cannot do this. If we're thinking, think about how this translates to code to generate data. There's nowhere to start, there's nowhere to end. It just goes in a circle and makes no sense whatsoever. So, this is the only trick question that I will give you this week. That's a promise. But there you go, and you saw through it, so very good. All right. So, you now know the basics of this little artistic procedure that some of us find helpful. You could, of course, go through your entire life without ever drawing one of these, but I think they're useful enough that it's worth us spending some time on. So let me just say quickly our take-home messages here. That generative model thing that we saw for the first time yesterday has all the information in it in principle that we need to either mock up fake data or do inference. So that's great. And that, in the back of your mind, you always remember, no matter how many approximations we're making, in principle, we're still encoding the entire process from some very far away object in the universe all the way through to the numbers on the computer that are constants and that we're not allowed to change. And hopefully you believe that PGMs are a helpful way of visualizing how models are constructed. And later on, of course, we'll see much more complicated things this week. And hopefully that will turn out to be the case. So there are some more exercises. These are things that, again, you should work on with one or two other people. They will take a bit more time. And I'm going to suggest we basically, even though there's not a notebook to work in as such, we transition into the sort of tutorial mode. So feel free to get up, get a drink of water, stretch your legs a little bit, come back and hack on these things. And maybe towards the end, or maybe after like half an hour, depending on how long it takes people, we'll come back together and draw a solution on the board. And we'll see if there's time for more than just this, but I'm not sure. Sound good? All right, let's do it. Wait, Adam's going to say something.
Yeah, I'm just going to re-emphasize, if you prefer to work on a whiteboard, which some of you may, they are scattered all over out there. Feel free to do that while working on this. But the invitation to go out there is to go out there and work. It is not the invitation to go out there and scroll on Twitter or check email. Okay, so we're working on problems for the next little bit.
So they are setting up for dinner out there, so it's very crucial that you don't get in the way. So if you want to work on a board, I'd say the chalkboards, there's a chalkboard on this wall just behind the screen. That's probably a good one to use, but maybe don't go down towards the dinner setup. And yeah, there's also this one here.
Yeah, we'll just bring this one up here.
You want to make an announcement now? Just like the probability that Adam announces probability.
Oh, sorry. There were specific questions that were not on the previous slide. And I can't show them both at once, so let me also say this whole notebook that I've been showing you, this is already in the repo for the DSFP sessions. You can grab it, and then you can see both the setup and what you are being asked to do at the same time, if you would like.
And it is especially important for this exercise that you work with someone. You should be talking the whole time you're working here, right? This doesn't require intense silence, right? Okay, thank you.
All right. Okay, everybody. We have, according to the clock, 10 minutes left. So I figure we should go over the solution to this one exercise. And if you want to entertain yourself with the remaining bonus exercises later on, that's up to you. So I'm assuming everybody can still see the two sides well enough that I can use the board here. So one thing that came up, and it might originally have been intentional, I don't remember, but the wording of this is fairly vague in that I've just sort of carelessly sketched out the usual least squares fitting a line to data problem without explicitly saying, for example, that we'd like to fit for the values of A and B. Which hopefully most of you intuited. And there are some other things that are not explicitly stated here, but which might be learning moments for either for you or for me in terms of how these things should be written. So let's together draw the PGM. By the way, when I said solutions, I still meant that you're going to have to tell me what the solution is. I'm not going to. So let's try and draw the PGM / write down some expressions together. Volunteers. Yo. There should be a rectangle somewhere. Good. Again, not something that was really totally explicitly stated here, but we definitely have a list of x's, y's, and sigmas. And so hopefully they're independent enough that we can get away with a rectangle. So let's do this. All right, somebody else. And where should I put it? Oh, yes, because there's a K. All right, I won't ask that every time. Good. What else? You could just randomly say the name of something which appears in the problem. Single.xk. Where? Good. I just said that I wouldn't. All right. xk with a dot. And why is there a dot? Or because I said that we should just assume that, right? Yes, okay. Excellent. Next. Actually, before that, should I connect these somehow? Oh, well, we only know one way of connecting them. And which direction? All right, good. Okay. What else should go into yk that we don't have on here yet? Sigma k, okay. It goes in here, and it is what kind of a node? Also a dot. Very good. Anything else? A and B. Where do I put A and B? Outside. And how do I... Oh, okay. Good, getting the hang of this. A and B. Is this okay? Well, I'm not sure what you're assuming either. But I didn't tell you one way or the other, so that's a perfectly good question to have. What I meant here, is this okay, is should I do this, or should I maybe do that? Did somebody say I should do both? I mean, again, I didn't tell you, but what do you think this means versus that option? With this one? Well, that's, yeah. I'm not sure I see the connection. Oh, yes, but remember there's the directionality here. So we are going from parameters to data eventually. I'm not sure that's a profitable path to direct our thoughts down. And to be fair, we didn't actually see anything like this earlier, right? This would be a choice that you would make. So basically what this is saying is there's A has a prior, B has a prior, and they're different things. They're independent. And this would say, I don't know why we would have this, but if we had a joint prior on A and B where the two were not dependent, where the prior on A was something, on A and B was something with some degeneracy, you would sort of have to stick them together there. That's all. But let's not make life hard. So let's do that. And now we have to connect these in somehow. Okay, we could do that. Does anyone object to doing that? This is not a leading question, but I would like to know the answer. Okay, I kind of like that. So no offense, but I'm going to do that. But it's totally fair either way. And as we write down the actual products of probabilities, this would come out in the wash if we've done everything right. So any preference for a letter that I should use?
Poop emoji.
I'm not a very good artist. Okay, delta. and, what, and what kind of node should it be, Adam? Okay. And it must be right because Adam said so. Okay, good. So in the remaining 3 minutes, I think we can manage this. Let's translate this into a sequence, or I guess a product of probabilities with things and then vertical bars and then other things. You know what I'm talking about, yeah. Oh, the X should also feed into the poop emoji if we do this. And then we shouldn't have, yes, very good, thank you. Okay. So next step is for me to write down P, open parentheses, and then wait patiently. Good, okay, P of A. And anything else or just A? I did not hear a coherent answer from anywhere in the room. Okay, I saw a head shaking, so we're gonna close the parentheses. Okay, so here we have A, nothing feeds into A, so there's some prior, you'll have to choose it in practice, but we don't actually have any data to work with, so who cares? And similarly, P of B, I guess it shows up exactly the same way. Next. Oh, we forgot one thing. Yes, thank you. I will actually not try to squeeze it in there. Exactly. Okay. P of delta K given A, B, and xk. And this is a delta function we said. So I'm not sure anybody said it out loud, or at least loud enough that everyone could hear. But what is this actually representing, this new thing that we've introduced? Well, the data would be the thing in the mean, right? So this is at a given x, what value of y is exactly on the line. And we know that the real data or the mock data will not be exactly on the line because of this guy. So, all right. I'm just going to say this is a plus b xk because I know that you have all figured that out. All right. Finishing us off in 15 seconds. Okay. And this in practice is what? Is the normal distribution. Okay, so I'm just going to say Gaussian with this mean and this standard deviation. Good. And we are missing one thing. Yeah, which we're not really missing, but anyway. P of xk, and that was given to us as a delta function, so actually forget that. Oh, P of sigma, yeah. Right. So in practice, if we're actually writing code, we're going to go like that, right?